Imagine standing on the edge of the unknown, staring up at a sky so vast it feels infinite. For centuries, humanity has reached toward the stars with a mix of wonder and determination, driven by an insatiable curiosity to uncover the secrets of the cosmos. Today, that quest is more alive than ever, as we stand on the brink of breakthroughs that could redefine not just our understanding of space, but our very future within it. This isn't just about exploration, it's about transformation. From colonies on Mars to probes venturing into the interstellar void, the next chapter of space exploration is packed with missions so ambitious they could alter the course of human history. Think about it, we're living in an era where dreams once confined to science fiction are becoming reality. Missions designed to mine asteroids for precious resources, telescopes capable of spotting signs of life on distant exoplanets, and even plans to establish permanent human settlements beyond Earth. These aren't just ideas anymore. They're real projects backed by cutting-edge technology and the brightest minds of our generation. And the craziest part, many of these missions are already underway, quietly unfolding in the background while we go about our daily lives. But here's what's truly exciting. Among the countless missions launching in the coming years, there are 30 that stand out not just for their ambition, but for their potential to change everything. Whether it's unlocking the mysteries of dark matter, paving the way for interplanetary travel, or discovering the first definitive proof of extraterrestrial life, these missions could rewrite textbooks, reshape economies, and even redefine what it means to be human. So buckle up, because we're about to take a deep dive into the most groundbreaking space missions on the horizon, each one a stepping stone toward a future that's stranger, bolder, and more awe-inspiring than anything we've dared to imagine. At the heart of humanity's next giant leap lies the Artemis program, NASA's boldest lunar endeavor since the Apollo era. But this isn't just a repeat of history, it's a revolution. By 2025, Artemis aims to land the first woman and the next man on the moon, marking the dawn of a sustainable human presence beyond Earth. Unlike the fleeting visits of the past, Artemis is building the infrastructure for long-term exploration, starting with the Lunar Gateway, a pioneering space station orbiting the moon. Think of it as a cosmic pit stop, a hub where astronauts can live, conduct research, and prepare for missions deeper into space. What makes Artemis truly groundbreaking is its vision for the future. The program isn't just about planting flags, it's about laying the foundation for humanity's journey to Mars. Scientists are testing cutting-edge technologies, from next-gen spacesuits to 3D printed habitats using lunar soil. Imagine astronauts living in structures built from the moon's own dust, or harvesting water ice from permanently shadowed craters, a vital resource for life support and even rocket fuel. These innovations aren't sci-fi fantasies, they're being developed right now with prototypes already in the works, but Artemis isn't a solo mission. It's a global collaboration, uniting space agencies from Europe to Japan and private companies pushing the boundaries of engineering. Together, they're proving that the next chapter of space exploration will be written not by one nation, but by all of humanity. Every rocket launch, every experiment, every footprint left in the lunar dust brings us closer to a future where the moon isn't just a destination, it's a springboard to the stars. Artemis isn't just about returning to the moon, it's about unlocking its potential as a galactic resource hub. Picture this lunar regolith, the dusty surface beneath astronauts' boots, packed with rare metals like titanium and helium-3, a fuel that could power future fusion reactors. Mining these resources wouldn't just fuel rockets, it could ignite an off-world economy, turning the moon into a pit stop for missions venturing farther into the solar system. Companies are already racing to develop robotic excavators and processing plants designed to operate in low gravity, proving this vision is closer than we think. But the Moon's real value might lie in its role as a testing ground for the technologies we'll need to survive on Mars and beyond. Its harsh environment, extreme temperatures, abrasive dust, and radiation makes it the perfect lab for stress testing everything from radiation shields to closed-loop life support systems. NASA experimenting with 3D printed habitats using lunar soil as building material, a technique that could one day allow settlers on Mars to construct shelters from the red planet's own dust. And let's not forget the water ice lurking in shadowed craters. If harvested, it could be split into oxygen for breathing and hydrogen for rocket fuel, essentially turning the Moon into a cosmic gas station. The ripple effects of Artemis stretch far beyond engineering. This mission could democratize space, sparking collaborations between governments and private companies in ways we've never seen. Imagine startups launching lunar delivery services or universities setting up research outposts alongside NASA bases. The Moon could become a shared workspace for humanity, where nations compete not for territory but for scientific breakthroughs. And perhaps most importantly, Artemis is rewriting the narrative of what's possible, inspiring a generation to look up not just in wonder, but with the conviction that the cosmos is within our reach. Every experiment conducted there, every resource extracted, brings us one step closer to a future where the Moon isn't just a milestone but a gateway. While the Moon serves as humanity's stepping stone, Mars holds the keys to answering one of our greatest questions. Did life ever exist beyond Earth? Enter the Mars Sample Return Mission, a staggering collaboration between NASA and the European Space Agency designed to do what no mission has done before: bring pieces of the red planet back to our labs. This isn't just about collecting rocks, it's about hunting for whispers of ancient life hidden within Martian soil, a quest that could rewrite our place in the universe. The mission's first act is already underway, with NASA Perseverance rover scouring Jezero crater, a dried-up river delta scientists believe once teemed with water. This robotic geologist isn't just taking photos, it's drilling core samples, sealing them in ultra-sterile tubes, and caching them like cosmic treasure chests. But here's where things get even more audacious. A second spacecraft will launch later this decade, carrying a nimble fetch rover to speed across Mars, tracking down Perseverance's samples and loading them into a rocket no bigger than a trash can. That's right, a rocket launching from another planet. Once in orbit, these precious samples will perform an intricate celestial handoff, transferring to a European-built orbiter that will shepherd them back to Earth. The stakes couldn't be higher. Back in labs equipped with tools far beyond what any rover carries, scientists will analyze these samples for molecular fossils, organic compounds, or even microbial remnants. Imagine holding proof that life isn't unique to Earth, a discovery that would ripple through science, philosophy, and culture. But the mission's genius lies in its backup plans. If fetch rovers fail, helicopters modeled after Ingenuity could retrieve tubes. If storms delay launches, samples can wait decades in their sterile vaults. This isn't just a mission, it's a multi-decade puzzle where every piece must click perfectly. Beyond pure science, Mars Sample Return is forcing breakthroughs in autonomous robotics and precision engineering technologies that'll shape future human expeditions. It's also sparking debates about planetary protection. How do we handle Martian material without contaminating Earth's biosphere? The answer: biosafety labs with multiple layers of containment, stricter than those used for Ebola. Every gram of Mars dust will be treated like both a scientific goldmine and a potential Pandora's box. What makes this mission unprecedented is its scope, blending the patience of archaeology with the precision of spaceflight and the daring of exploration. Success could reveal that life arose independently on two planets in one solar system, hinting that the universe is teeming with biology. Failure, even that, would teach us invaluable lessons about the audacity of interplanetary logistics. One thing's certain: when those samples finally land on Earth, humanity will hold in its hands not just Martian soil, but perhaps the answer to whether we're alone in the cosmos. Bringing Mars to Earth sounds like science fiction until you consider the risks. The biggest fear, contamination, not of Mars but of our own planet. Imagine uncovering traces of ancient Martian microbes only to realize they could interact unpredictably with Earth's ecosystems. That's why NASA and ESA are designing the sample return capsule like a biological fortress, with multiple layers of seals and sterilization protocols rivaling high-security labs. Even the act of opening these tubes will happen in specialized facilities under stringent conditions, treating every speck of Martian dust as both a scientific treasure and a potential threat. But contamination isn't the only hurdle. The mission's technical complexity is staggering, an interplanetary relay race with zero margin for error. The Fetch rover must navigate Mars' rugged terrain autonomously, locate sample tubes the size of soda cans, and load them into a petite rocket that's never been test-fired on Earth. Then there's the orbital dance. That rocket must launch flawlessly, rendezvous with a waiting spacecraft, and transfer its cargo mid-flight millions of miles from any human help. Even a single misaligned sensor or software glitch could doom decades of work. Yet the potential payoff is worth every risk. These samples could hold organic molecules or fossilized remnants of microbial life, evidence that Earth isn't the only cradle of biology. Picture scientists uncovering patterns in Martian clay that mirror early Earth's fossilized bacteria, a discovery that would reshape astrobiology overnight. And even if the samples reveal no life, their chemistry could expose how Mars transitioned from a watery world to a barren desert, offering clues about our own planet's climate future. The mission's boldness lies in its refusal to compromise. Instead of settling for limited data from rover instruments, it bets everything on bringing Mars secrets home, where labs can probe them with tools too massive for spacecraft. It's a gamble that mirrors humanity's greatest explorations, daunting, uncertain, but with the power to redefine what we know about life itself. Every obstacle overcome in this mission isn't just solving a problem, it's paving the way for the day when astronauts will walk those same dusty plains, searching for answers in person. While Mars sample return digs into our solar system's past, the James Webb Space Telescope peers across the cosmos, revealing secrets no human eye has ever seen. Launched on Christmas Day 2021 after decades of development, Webb isn't just another telescope, it's a time machine. Its gold-coated mirrors, wider than a tennis court, capture infrared light that's been traveling for billions of years, letting us witness the universe's infancy. And the images it's already delivered aren't just beautiful, they're rewriting astronomy textbooks. Take the famous cosmic cliffs in the Carina Nebula. Webb's infrared vision pierced through dust clouds that hid stellar nurseries from Hubble, exposing newborn stars carving valleys into space with their violent stellar winds. Then there's the groundbreaking spectrum of exoplanet WASP 96b, where Webb detected water vapor and even clouds in an alien atmosphere over 1,000 light-years away. This wasn't just a scientific first, it proved we can study the weather on distant worlds, bringing us closer to finding habitable planets. But Webb's most mind-bending discoveries might still lie ahead. Its instruments are finely tuned to hunt for biosignatures, molecules like oxygen or methane that could hint at life on exoplanets. Picture this: a distant Earth-like world crosses its star, and Webb's spectrographs catch the chemical fingerprint of forests or algae in its atmosphere. Even more provocatively, Webb could spot technosignatures, unexplained atmospheric pollutants or artificial heat signatures that might betray the presence of advanced civilizations. While that scenario remains a long shot, the telescope's ability to detect such anomalies is unprecedented. Beyond alien hunting, Webb is unraveling cosmic mysteries closer to home. It's pinpointing the earliest galaxies ever seen, some so ancient they shouldn't exist under current models, forcing astronomers to rethink how galaxies form. Other targets include the supermassive black holes at galaxy cores, where Webb's infrared eyes can observe the violent dances of matter spiraling into oblivion. Every new dataset it beams back doesn't just answer questions, it spawns new ones, pushing the boundaries of what we thought possible. What makes Webb revolutionary isn't just its technology, but its collaborative spirit. Built by NASA, ESA, and the Canadian Space Agency, it's a testament to what humanity can achieve when we unite across borders. Unlike Hubble's initial blurry vision, Webb worked flawlessly from day one, a triumph of engineering that's already surpassing its 10-year mission lifespan. And with projects like Cosmos Webb mapping 500,000 galaxies in unprecedented detail, this telescope isn't just observing the universe, it's helping us navigate our place within it. Each snapshot it captures isn't merely data, it's a puzzle piece in the grandest story of all the origin of everything. The James Webb Space Telescope's observations have only scratched the surface of its potential. Among its most eagerly anticipated targets, the TRAPPIST-1 system, a cosmic neighborhood just 39 light-years away with not one, but 7 Earth-sized planets, 3 of which orbit snugly within the star's habitable zone. Unlike anything in our solar system, these worlds huddle close together, some so near that standing on one would reveal neighboring planets hanging in the sky like oversized moons. Webb's infrared eyes will dissect their atmospheres with unprecedented precision, hunting for telltale gases like carbon dioxide, methane, or most tantalizingly, oxygen. Finding an atmosphere rich in oxygen and water vapor on a temperate rocky planet could be the closest we've come to detecting conditions ripe for life beyond Earth. But TRAPPIST-1 is just the beginning. Webb is also turning its gaze toward the enigma of dark matter, the invisible scaffolding that shapes the universe. By observing how distant galaxies warp light around them through gravitational lensing, scientists hope to map dark matter's distribution with finer detail than ever before. Picture this: Webb captures a distant galaxy cluster bending light like a funhouse mirror, revealing the unseen mass distorting spacetime. These observations could finally narrow down whether dark matter consists of yet undetected particles or if we're missing something fundamental about gravity itself. Then there's Webb's upcoming deep dive into the Kuiper belt, where mysterious objects like Arakoth, a primordial peanut-shaped relic from the solar system's birth, hold clues about how planets assemble. Its infrared sensors will analyze the chemical fingerprints of these icy bodies, potentially uncovering organic molecules that might have seeded life on Earth. Meanwhile, closer to home, Webb will scrutinize Europa and Enceladus, moons with subsurface oceans, measuring the composition of their watery plumes for hints of hydrothermal activity, a potential haven for microbial life. The telescope's versatility is its superpower. One week it might study the violent birth of stars in the Tarantula Nebula. The next, it could analyze the weather patterns on a scorching exoplanet where clouds rain molten metal. And let's not forget its role in cosmology. By pinpointing the universe's expansion rate with fresh data, Webb might resolve the Hubble tension, a nagging discrepancy in measurements that threatens to upend our understanding of cosmic evolution. What makes Webb's future so thrilling is its capacity for surprise. Like Hubble before it, some of its greatest discoveries will likely come from targets no one thought to prioritize, a faint smudge in the background of an image that turns out to rewrite astrophysics. Every new observation is a roll of the dice with the potential to turn impossible into inevitable. Whether it's spotting the glow of a distant city or unraveling the fabric of space-time, Webb isn't just a tool for science, it's a beacon guiding us toward the next frontier of cosmic understanding. Beneath Europa's frozen crust lies an ocean, not just any ocean, but one holding twice the volume of Earth's seas combined. This isn't science fiction. NASA Europa Clipper is gearing up to unveil the secrets of Jupiter's enigmatic moon, where towering geysers blast water into space through cracks in ice thicker than continents. Slated for launch in 2024, this spacecraft won't just fly by. It's designed for 45 close passes, skimming as low as 15 miles above Europa's surface, its instruments scanning for clues about what lurks in those pitch-black waters below. What makes Europa so compelling isn't just the presence of water, but its chemistry. Hubble spotted plumes erupting near the Moon's south pole, suggesting hydrothermal vents might churn on its seafloor, environments eerily similar to Earth's deep-sea ecosystems where life thrives without sunlight. Clipper's mass spectrometers will taste these ejected particles, hunting for organic molecules like amino acids. Meanwhile, ice-penetrating radar will map the ocean's depth and salinity, while thermal imagers pinpoint hotspots where liquid might surge to the surface. But here's the kicker. If microbial life exists in Europa's abyss, traces could be frozen into surface ice or ejected in those plumes, waiting for Clipper to detect them. The mission's boldest ambitions hinge on a proposed companion, a lander. Picture a nuclear-powered drill melting through ice, lowering a robotic submersible into the alien ocean, a concept straight out of Arthur C. Clarke's 2001. While not yet funded, engineers are already testing drills that could penetrate miles of ice, armed with sterilized sensors to avoid contaminating potential ecosystems. Even a shallow drill could analyze surface ice for cryovolcanic snow, material that once floated in the ocean below, but Europa isn't making exploration easy. Bathed in Jupiter's intense radiation, the Moon fries electronics like a cosmic microwave, forcing Clipper to dart in and out, gathering data in bursts. Its aluminum vault shields instruments with the same material used in bulletproof vests, while its orbit exploits gravitational assists from sister moons Ganymede and Callisto to minimize exposure. Every flyby is a high-stakes balancing act. Too close and radiation could cripple the spacecraft. Too far and it might miss crucial plumes. What sets this mission apart is its potential to answer a question that's haunted humanity for millennia: are we alone? Unlike Mars, where we hunt for fossils of ancient life, Europa's ocean might still teem with organisms today. Finding even simple microbes there would suggest life isn't a fluke of Earth, it's a cosmic inevitability. And if Clipper's data reveals hydrothermal activity or complex chemistry, the next step could be a lander targeting those icy geysers, where fresh ocean material sprays ready-made for analysis. Beyond biology, Europa holds lessons about how oceans form on icy worlds, knowledge that could apply to Saturn's Enceladus or distant exoplanets. Clipper's findings might reveal whether these subsurface seas are temporary phenomena or stable for billions of years, expanding our understanding of habitable zones in the universe. Every salty plume sampled, every thermal vent mapped, brings us closer to knowing whether Earth's vibrant biosphere is unique or just one ripple in a vast ocean of life. Imagine a world where rain falls not as water but as liquid methane, where rivers carve valleys through dunes of plastic like sand, and where the sky glows orange under a haze thicker than smog. This isn't a fantasy, it's Titan, Saturn's largest moon, and NASA, a Dragonfly mission, is about to turn this alien landscape into a real-life exploration ground. Slated to launch in 2027, Dragonfly isn't just another rover, it's a nuclear-powered drone, a rotorcraft designed to hop across Titan's surface like a robotic dragonfly, uncovering secrets about the chemistry that might have sparked life elsewhere in the universe. What makes Titan so extraordinary is its eerie resemblance to early Earth, but with a twist. Instead of water, its hydrologic cycle runs on methane and ethane, with lakes and seas of these hydrocarbons dotting its poles. But the real magic lies in its atmosphere, rich in nitrogen and organic compounds, constantly cooking up complex molecules under the moon's thick orange haze. Scientists call it probiotic chemistry, the same kind of reactions that likely set the stage for life on our planet billions of years ago. Dragonfly's mission: to land near Titan's equator at the Selk impact crater, a site where water and organic materials may have once mixed, and then embark on a series of flights, each lasting up to 8 kilometers, to sample and analyze this alien cocktail. The drone's design is a marvel of engineering. With 8 rotors stacked in pairs, it's built to navigate Titan's dense atmosphere 4 times thicker than Earth's, which makes flying easier despite the Moon's low gravity. Imagine a helicopter the size of a compact car, but far lighter, powered by a radioisotope thermoelectric generator that converts heat from decaying plutonium into electricity. This lets Dragonfly operate even in Titan's frigid -180 degrees Celsius conditions, where solar power would be useless. Each hop is a calculated risk. The drone will spend Titan's 16-day-long afternoons recharging and analyzing samples before taking off again at dawn, using terrain mapping cameras and spectrometers to choose its next target. But Dragonfly's true mission is to play detective in the greatest chemical mystery of all: how lifeless molecules become the building blocks of biology. Its instruments will sniff out complex organics like amino acids and nucleotides, hunting for clues about how these compounds form and interact in Titan's methane-rich environment. One tantalizing possibility: the drone could find azotosomes, hypothetical cell-like structures theorized to form in liquid methane instead of water. While these wouldn't be life as we know it, their discovery would prove that the universe has more than one recipe for complexity. Dragonfly's journey won't be solitary. As it flies, it'll compare its findings to data from the Cassini-Huygens mission, which dropped a lander on Titan in 2005. That probe revealed river channels and shorelines, but Dragonfly will go further, exploring dunes, craters, and even cryovolcanoes that might spew icy slurry from Titan's subsurface ocean. Some scientists speculate this hidden sea could be another potential habitat, separated from the surface by miles of ice but warmed by tidal forces from Saturn's gravity. What sets Dragonfly apart from any past mission is its audacity. Instead of rolling slowly across a landscape, it's leaping into the unknown, turning Titan's thick air into a highway. Every flight is a chance to rewrite our understanding of chemistry's potential beyond Earth. And if it finds even hints that Titan's environment could foster life-like processes, whether water-based or methane-based, it would shatter our assumptions about where life could exist in the cosmos. By the time Dragonfly completes its 2.5-year odyssey, we may not just know more about Titan, we might have glimpsed the universal rules that turn chemistry into biology, and in doing so, redefined what it means to be alive. Perched high in Chile's Atacama Desert, the Vera C. Rubin Observatory is about to transform our understanding of the cosmos, not by staring at one patch of sky, but by capturing all of it every single night. This isn't just another telescope, it's the ultimate cosmic surveillance system, equipped with the largest digital camera ever built for astronomy, a 3,000-megapixel behemoth that can spot a golf ball from 15 miles away. When it begins its 10-year legacy survey of space and time in 2025, Rubin will generate more data in its first week than all previous astronomical surveys combined, unveiling a universe far more dynamic and mysterious than we ever imagined. At the heart of its mission is the hunt for dark energy, the elusive force accelerating the universe's expansion. Rubin's wide-field camera will map billions of galaxies, tracking how their distribution has shifted over cosmic time. By measuring the subtle warping of light around these galaxies, a phenomenon called weak gravitational lensing, scientists hope to decode dark energy's fingerprints, potentially revealing whether it's a constant force or something that evolves. Picture this: Rubin's data might show galaxies clustering differently at various epochs, hinting that dark energy's strength has changed over billions of years. That could upend everything we know about cosmology, forcing us to rewrite Einstein's theory of gravity itself. But Rubin's eyes won't just be fixed on the distant universe. Closer to home, it's about to become Earth's first line of defense against asteroids. The telescope will detect tens of thousands of previously unknown near-Earth objects, some of which could pose existential threats. Its rapid scanning ability means it can catch asteroids as small as a house weeks before they approach crucial time to deflect a potential impactor. And it's not just rocks Rubin will spot. Its sensitivity might reveal interstellar visitors like Oumuamua, the cigar-shaped object that zipped through our solar system in 2017. Imagine identifying dozens more of these cosmic nomads, each one a postcard from another star system carrying secrets about how planets form in alien environments. What sets Rubin apart is its appetite for the unpredictable. Most telescopes focus on predetermined targets, but Rubin will catch cosmic fireworks in real-time, supernovas exploding, stars being shredded by black holes, even the elusive optical counterparts to gravitational wave events. It's like having a security camera pointed at the entire universe, ready to alert astronomers the moment something unusual happens. And with machine learning sifting through its avalanche of data, Rubin could uncover phenomena we haven't even theorized yet, perhaps objects that warp spacetime in ways no model predicts, or mysterious flashes that defy known physics. The observatory's design is as groundbreaking as its goals. Its mirror, wide enough to fit 7 people lying head to toe, collects light with unprecedented efficiency, while its camera's filters span from ultraviolet to near-infrared. Each 15-second exposure captures an area of sky 40 times larger than the full moon, and over a decade, Rubin will image every accessible part of the southern sky nearly 1,000 times. This time-lapse of the universe will reveal motion at scales never seen. Stars drifting, asteroids tumbling, galaxies rotating. Even the Milky Way will come alive in 3 dimensions as Rubin pinpoints millions of stars with distances measured to within 1% accuracy. Yet Rubin's true legacy may lie in its open data philosophy. Unlike traditional observatories that restrict access, Rubin will broadcast its discoveries in near real time, allowing amateur astronomers and school kids to explore the same data as professionals. This democratization of discovery means the next groundbreaking observation might come from a teenager spotting an anomaly on their laptop. And with anticipated discoveries ranging from new dwarf planets in our solar system to quasars at the edge of the observable universe, Rubin isn't just a telescope, it's a gateway to the unknown, reminding us that the night sky isn't static, but a stage where the universe's greatest dramas unfold nightly, waiting for us to notice. Picture a telescope so powerful it could spot a city's streetlights on a planet orbiting another star. That's the promise of Lunar, a most ambitious space observatory concept yet, a colossal eye in the sky designed to do what no instrument has achieved, directly photograph Earth like worlds and sniff their atmospheres for signs of life. Short for the Large Ultraviolet Optical Infrared Surveyor, this behemoth isn't just an upgrade to Hubble or Webb, it's a quantum leap, with a mirror up to 15 meters wide, dwarfing Webb's 6.5-meter span. To grasp its scale, imagine a mirror so large it couldn't fit inside a tennis court, unfolding in space like a high-tech origami masterpiece. The mission's crowning achievement would be its ability to isolate pale blue dots from the glare of their host stars, a feat akin to spotting a firefly hovering next to a searchlight. While Webb studies exoplanets by analyzing starlight filtered through their atmospheres during transits, Lunar could capture their actual light, separating it from the stellar glare with a sunflower-shaped starshade or advanced internal coronagraph. This means studying planets that don't transit, vastly expanding our hunting grounds for habitable worlds. Imagine seeing the swirling clouds of a distant Earth twin, or mapping continents and oceans on a world dozens of light years away. But Lunar's real magic lies in spectroscopy. By dissecting the light from these exoplanets, it could detect molecular oxygen, methane, or even chlorophyll potential biosignatures hinting at forests or algae. One tantalizing target, Proxima Centauri b, a rocky planet in the habitable zone of our nearest stellar neighbor. Lunar might reveal whether its ruddy sunlight fuels photosynthesis or if its atmosphere shows industrial pollutants, subtle clues of a technological civilization. The telescope's ultraviolet vision could also spot ozone layers, while its infrared sensors hunt for heat signatures of cities or vast farmlands. Beyond alien hunting, Lunar would revolutionize every field of astronomy. Its resolution could zoom in on the event horizon of black holes in distant galaxies, watch gas clouds collapse into stars in real time, or trace the birth of heavy elements in supernova explosions. It might even settle the debate over the universe's expansion rate by measuring distant supernova with pinpoint accuracy. And unlike Webb's fixed lifespan, Lunar is designed for servicing astronauts or robots could upgrade its instruments, keeping it cutting edge for decades. The catch: Lunar is still a concept competing for funding in NASA's crowded mission pipeline. If selected, it wouldn't launch until the 2040s. Yet the technology isn't sci-fi. Prototypes of its deformable mirrors and starshades are already being tested in vacuum chambers. Every hurdle overcome brings us closer to an era where we might gaze at another Earth's weather patterns or catch the glow of alien city lights, a humbling reminder that we're not just explorers of space, but guests in a galaxy that might teem with neighbors. Sending spacecraft to another star within a human lifetime sounds like pure fantasy until you hear the numbers behind breakthrough Starshot. This isn't science fiction, it's hard physics with a bold vision, flinging gram-sized probes toward Alpha Centauri at 20% the speed of light, reaching our nearest stellar neighbor in just 20 years. Picture this: thousands of wafer-thin nanocrafts, each no heavier than a paperclip, propelled by a phalanx of Earth-based lasers packing 100 gigawatts of power, more energy than all sunlight hitting New York City at noon. The secret lies in light sails, an idea championed for decades but never at this scale. These aren't the bulky sails of old proposals. They're micrometer-thin sheets of metamaterials designed to reflect laser light with near-perfect efficiency. When that concentrated beam hits a sail, the pressure of photons, yes, light itself, shoves the probe forward with steady acceleration, hitting mind-bending speeds within minutes. Engineers liken it to using a stadium's worth of floodlights to push a postage stamp, but scaled up to interstellar distances. The sail must withstand forces that would vaporize ordinary materials, all while steering with precision finer than a human hair's width to stay centered in the laser's crosshairs. Each nanocraft carries a payload barely visible to the naked eye. Cameras the size of a grain of salt, atom-scale spectrometers, and even miniature thrusters fueled by microscopic pellets. Their job: snapping photos of Proxima Centauri b as they zoom past at 44,000 miles per second, collecting data on atmospheric composition, surface features, and potential biosignatures. The real challenge: getting those signals back to Earth. Imagine a transmitter weaker than a smartphone's Wi-Fi, broadcasting from 4.3 light-years away. Breakthrough's solution: a laser communication system powered by the sail itself, each photon carrying bits of data across the void, captured by telescopes the size of football fields waiting here at home. The timeline is just as staggering as the tech. Within 5 years, prototypes could test laser acceleration in Earth's orbit. A decade later, a full-scale light sail might make a flyby of Pluto, proving the concept at solar system distances. By 2050, if funding and physics align, the first swarm could launch toward the stars, their sails folding like origami during the decades-long cruise before unfurling for the critical encounter. What makes Starshot revolutionary isn't just the engineering, it's the philosophy. Instead of betting everything on one fragile probe, this mission embraces failure by design. Launch thousands, even if 99% fail, the survivors could rewrite our understanding of exoplanets. And while Alpha Centauri is the first target, the same tech could one day reach TRAPPIST-1 or other nearby stars, turning interstellar exploration from a dream into a routine. Every technical hurdle overcome, from perfecting laser arrays to shielding sails from cosmic dust, is a step toward a future where the stars aren't just points of light but destinations. The project's biggest obstacle isn't just power or speed, it's patience. Unlike Mars rovers sending daily updates, Starshot's probes would vanish into the dark for 20 years before their one-shot flyby. But if successful, humanity might wake up one morning to images of alien coastlines or methane seas, transmitted by machines smaller than a coin. That's the gamble, investing billions today for a postcard that might not arrive until 2070, proving that the universe isn't out of reach, just waiting for us to think small enough to go big. While telescopes have evolved from Galileo's crude spyglasses to city-sized radio arrays, one project aims to leapfrog them all by turning the moon itself into a cosmic listening device. NASA's Lunar Crater Radio Telescope isn't just another instrument. It's an audacious plan to transform a natural lunar depression into a dish over half a mile wide, dwarfing even China's 500-meter fast telescope. The concept is deceptively simple. Land a swarm of climbing robots on the far side of the moon, have them deploy a wire mesh across a carefully selected crater, and voila, you've got a radio telescope shielded from Earth's noisy civilization, poised to capture whispers from the universe's infancy. The far side of the moon offers what astronomers can only dream of on Earth: perfect radio silence. Our planet's ionosphere reflects some frequencies while human-made interference, from Wi-Fi to satellites, drowns out others. But on the lunar far side, shielded by 2,000 miles of solid rock, this megatelescope could tune into cosmic static from 13.8 billion years ago, when the first stars flickered to life after the Big Bang. Scientists call this the Dark Ages, that mysterious epoch before starlight flooded the cosmos, when the universe was filled with neutral hydrogen atoms emitting faint 21-centimeter radio waves. Detecting those primordial signals would be like finding a recording of the universe's first breath, revealing how chaotic hydrogen soup condensed into the first galaxies. Engineering this behemoth requires tricks straight out of science fiction. Instead of hauling heavy structures from Earth, NASA's plan calls for dual-axle rovers, four-wheeled bots that can split in two, with one half anchoring while the other rappels down crater walls trailing conductive wire. Picture these mechanical spiders weaving a spiderweb of aluminum across the lunar terrain, creating a parabolic reflector precise enough to catch wavelengths longer than a blue whale. No lander could carry a rigid dish this size, but by using the moon's own geography as scaffolding, scientists exploit nature's ready-made solution. What makes this mission extraordinary isn't just its scale, it's the frequencies it can access. Earth's atmosphere blocks signals below 30 megahertz, but the moon's vacuum lets the Lunar Crater Telescope tune down to a mere 100 kilohertz. This opens a window into exotic phenomena, the magnetic fields of distant exoplanets, the death throes of ancient black holes, even hypothetical dark matter particles decaying into radio waves. Some theorists speculate it might catch stray transmissions from extraterrestrial civilizations, though that's not its primary goal. The project's challenges are as vast as its potential. Micrometeorites could puncture the delicate mesh. Temperature swings from -170 to 130 degrees Celsius might warp materials. And without humans nearby, repairs would depend on autonomous robots, a technology still in its infancy. Yet NASA's Innovative Advanced Concepts program has funded feasibility studies, and teams are already testing mesh deployments in simulated lunar craters on Earth. If successful, this telescope could rewrite cosmology's opening chapters. By mapping how hydrogen fog clustered in the early universe, it might reveal why matter clumped into galaxies instead of dispersing evenly. It could even spot anomalies suggesting our universe collided with another in a long-ago multiverse event. More practically, the mission would pioneer techniques for turning alien landscapes into scientific tools, a blueprint for future telescopes in Martian craters or floating in Venus's atmosphere. The Lunar Crater Radio Telescope embodies a paradigm shift in exploration. Instead of bringing our instruments to space, we're learning to build them from what's already there. Every crater on the Moon becomes a potential observatory, every lava tube a possible habitat. As we inch closer to making this megatelescope reality, we're not just expanding our view of the cosmos, we're reimagining how humanity might harness the solar system itself as the ultimate workshop. Deep in the asteroid belt between Mars and Jupiter drifts a world unlike any other Psyche, a 230-kilometer wide metallic behemoth that might hold the exposed heart of a failed planet. NASA's namesake mission to this bizarre asteroid isn't just another space rock rendezvous. It's an interplanetary archaeology dig, aiming to uncover clues about the violent collisions that shaped our solar system 4.5 billion years ago. Scheduled to arrive in 2029 after a 2.5 billion-mile journey, the Psyche spacecraft will orbit this metallic relic for 21 months, mapping its composition with instruments so precise they could distinguish a dime's thickness from 60 miles away. What makes Psyche extraordinary isn't just its size, it's what it's made of. Unlike stony or icy asteroids, Psyche appears to be almost entirely metal, with spectral data suggesting an alloy of iron and nickel laced with gold, platinum, and other rare elements. Scientists suspect it could be the stripped core of a protoplanet, a would-be world whose outer layers were blasted away by ancient impacts, leaving behind a celestial skeleton. If true, studying Psyche would be like getting a hands-on look at Earth's own unreachable core, which lies 3,000 kilometers beneath our feet under crushing pressure. The asteroid's surface might bear scars from these primordial collisions, canyons carved by molten metal flows, or magnetic fields frozen into place as the core cooled. The mission's toolkit reads like a sci-fi wish list. A gamma-ray neutron spectrometer will scan for elemental fingerprints, revealing whether Psyche's metal matches predictions for planetary cores. Multispectral imagers will hunt for patches of surviving silicate mantle material, hints of the rocky shell that once encased this metallic heart. But the real showstopper is the magnetometer, designed to detect any remnant magnetic field. Earth's magnetic dynamo comes from its swirling liquid outer core, so if Psyche's frozen metal still carries magnetism, it could confirm the asteroid was once molten and dynamic, just like our planet's interior. Beyond pure science, Psyche tantalizes with practical possibilities. The asteroid's metal content could be worth quadrillions of dollars if mined, though that's not NASA's goal. Instead, the mission is sparking debates about how such resources might one day be harvested without exhausting Earth's own reserves. Startup space mining companies are already studying Psyche's data, envisioning future refineries in zero gravity where metals are extracted without the environmental toll of terrestrial mining. The engineering behind this mission is just as audacious as its science. To reach the asteroid belt, the spacecraft is riding a super-efficient solar electric propulsion system, ion thrusters that accelerate xenon particles to 75 miles per second, emitting an eerie blue glow. These whisper thrust engines are too weak to lift a piece of paper on Earth, but in frictionless space, they build speed relentlessly for years. Psyche will also test laser communication technology, beaming data back to Earth at rates comparable to broadband internet, a crucial upgrade for future deep space missions. Perhaps the most profound question Psyche might answer is how planets get their metal cores in the first place. Current theories suggest they form when dense metals sink through molten rock during a world's infancy, but no one has ever seen the process in action. Psyche could be the smoking gun, showing us exactly what a baby planet's core looks like frozen in time. Even if it turns out to be something stranger like a pile of metal rubble from an apocalyptic collision, the findings would rewrite models of solar system formation. As the spacecraft closes in on its target, it won't just be studying an asteroid, it'll be peering into the very building blocks of worlds. Every crater on Psyche's metallic surface tells a story of ancient violence, every magnetic anomaly a clue about how planets like ours became habitable. And if this mission succeeds, we won't just understand Psyche better, we'll understand our own place in the cosmos and how rare, precious worlds like Earth came to be. Venus hides its secrets beneath a crushing blanket of acid clouds where temperatures melt lead and pressures flatten submarines. But NASA Da Vinci I+ mission is daring to plunge straight into this inferno, not just to survive it, but to decode the planet's most baffling mysteries. Picture a spacecraft shaped like a flying saucer, hurtling into Venus's sulfuric haze at 24,000 miles per hour before unfurling a parachute the size of a baseball diamond. As it drifts downward through layers of corrosive vapor, its instruments will perform the most detailed chemical analysis ever conducted on another planet's atmosphere, hunting for clues about everything from phantom phosphine gas to the slim but tantalizing chance of life floating in those toxic skies. The mission's crown jewel is its descent sphere, a titanium-clad laboratory built to withstand conditions that would vaporize most electronics in seconds. Inside, laser spectrometers will zap passing gas molecules, measuring their atomic signatures with precision finer than a lab on Earth. One prime target: phosphine, a stinky, flammable gas that shouldn't exist in Venus's clouds without some exotic chemistry or just maybe microbial activity. When telescopes detected traces of it in 2020, the scientific world erupted with theories from unknown geologic processes to floating extremophiles. Da Vinci I+ won't just confirm whether phosphine is really there, it'll track how its concentrations shift at different altitudes, potentially revealing whether it's being replenished by hidden vents or biological processes. But phosphine is just the beginning. The probe's sensors will dissect Venus's atmosphere like a cosmic layer cake, analyzing how sunlight interacts with sulfuric acid droplets at different heights. Some scientists suspect these droplets might harbor hardy microbes similar to Earth's acid-loving bacteria, which thrive in volcanic craters and toxic mines. The spacecraft's ultraviolet imager will scan for unusual cloud patterns, patchy streaks, or splotches that could hint at organic material drifting aloft. Even if life isn't found, understanding how complex molecules behave in such extreme conditions could reshape our search for habitable worlds, revealing how chemistry dances at the edge of impossibility. What makes Da Vinci I+ revolutionary isn't just its instruments, it's how it thinks on the fly. Unlike static landers, the probe will adjust its sampling in real time as it falls, prioritizing unexpected chemical signatures detected higher up. Imagine it sniffing a whiff of ammonia or hydrocarbons mid-descent and immediately redirecting its spectrometers to investigate capabilities that could turn a single plunge into dozens of discoveries. And when it finally succumbs to the surface's 900-degree furnace, its last act will be measuring the composition of a mysterious metallic snow that might blanket Venus's mountains, possibly a mix of bismuth sulfide and other exotic minerals condensed from the boiling atmosphere. Beyond pure science, this mission could settle one of astronomy's oldest debates. Was Venus once an Earth-like oasis? Da Vinci I+ will measure isotopes of hydrogen and oxygen in water vapor, hunting for signs that the planet lost oceans billions of years ago. If certain heavy isotopes dominate, it would confirm that lighter water molecules escaped into space, leaving behind a dehydrated hellscape. That data could reveal whether Venus crossed a climate tipping point, a chilling warning for our own planet's future. Every measurement Da Vinci I+ beams back will peel away another layer of Venus's enigma. Whether it uncovers alien biochemistry or simply rewrites our models of atmospheric chemistry, one thing's certain: by staring into the furnace of our sister planet, we're not just exploring Venus, we're holding up a mirror to Earth's own fragile place in the cosmos. Imagine a world where our energy doesn't come from smoky power plants or sprawling solar farms, but from massive satellites in space, soaking up sunlight 24/7 and beaming clean electricity back to Earth, rain or shine, day or night. This isn't a far-off fantasy. It's the vision behind space-based solar power, a radical solution gaining traction with the European Space Agency and institutions like Caltech. The concept is simple yet revolutionary. Launch solar panels into orbit where they can harvest sunlight uninterrupted by clouds or nightfall, then transmit that energy wirelessly to receiving stations on the ground. The potential is staggering, unlimited, on-demand clean energy that could finally wean humanity off fossil fuels and slow the march of climate change. The European Space Agency's Solaris initiative is one of the most ambitious efforts to turn this idea into reality. Their plan involves constructing kilometer-scale solar arrays in geostationary orbit where they'd bask in constant sunlight. These arrays wouldn't just collect energy, they'd convert it into microwaves or lasers and beam it down to giant receiver grids on Earth with pinpoint accuracy. Picture a desert installation covered in Rectina's special antennas that convert microwave energy back into electricity, quietly powering entire cities without a single smokestack in sight. ESA estimates a single orbital solar farm could generate as much power as a nuclear plant, with none of the radioactive waste or fuel shortages. Meanwhile, Caltech's space solar power project is pushing the boundaries of engineering with its lighter-than-air designs. Their prototype, launched in early 2023, tested ultra-lightweight solar panels that unfold like origami in space, paired with groundbreaking wireless power transmission tech. The key innovation: their system uses phased arrays, thousands of tiny transmitters that synchronize their signals to steer energy beams precisely across thousands of miles without moving parts. It's the same principle behind military radar systems, but harnessed for peaceful energy delivery. Caltech's experiments have already proven they can beam detectable power from orbit, a crucial first step toward scaling up. The challenges are as immense as the rewards. Building solar satellites requires launching thousands of tons of material into space, a logistical nightmare with current rocket prices. That's why proponents are banking on reusable launch systems like SpaceX's Starship to slash costs. Then there's the transmission puzzle. Even a tightly focused energy beam disperses over long distances, meaning ground stations would need to sprawl across miles to catch enough power. Safety concerns linger too. Though the beams operate at intensities no stronger than sunlight, regulatory agencies will demand ironclad proof they can't accidentally fry airplanes or birds passing through. What makes these projects so compelling isn't just their tech, it's their timing. As climate change accelerates, space solar power offers a rare win-win, decarbonizing energy grids while meeting soaring global demand. Unlike terrestrial renewables, it's not limited by geography or whether orbital arrays could deliver power to disaster zones, remote mines, or even future lunar bases. And while the upfront costs are eye-watering, advocates point out that fossil fuel subsidies already top $5 trillion annually. Redirecting a fraction of that investment could bootstrap an entirely new energy economy. The road ahead is long, but the pieces are falling into place. Private companies like Airbus and Northrop Grumman are joining the race, testing modular panel designs and high-efficiency converters. Some visionaries even dream of sourcing materials from the moon, where low gravity could make launching solar satellites far cheaper. Whether this becomes humanity's next giant leap or a cautionary tale of overreach depends on breakthroughs we're making right now. One wireless power transmission, one lightweight panel, one orbital test at a time. If successful, we might look back at oil derricks and coal mines the way we view steam engines today, relics of a darker, dirtier age before we learned to harvest fire from the sky. Mars has long been humanity's next frontier, but how we settle the red planet depends on who you ask, and the visions couldn't be more different. On one side, SpaceX's Elon Musk paints a picture of a bustling Martian metropolis, where fleets of starships ferry settlers to a self-sustaining city under glass domes. On the other, NASA envisions tightly controlled scientific outposts where astronauts conduct research in modular habitats before returning home. Both share the same hostile environment, yet their approaches reveal a fascinating divide between expansion and exploration, between making Mars a second home and treating it as the ultimate field station. SpaceX's vision hinges on Starship, a fully reusable colossus designed to carry 100 colonists at a time. The goal isn't just survival, but civilization. Think geodesic domes pressurized with local CO2, underground tunnels carved by autonomous boring machines, and greenhouse towers growing food under artificial sunlight. Musk's timeline is notoriously optimistic. He's hinted at boots on Mars by 2030, but the engineering is dead serious. Starships would double as initial habitats, their stainless steel hulls repurposed into living quarters while settlers construct more permanent structures. The real game changer, in situ resource utilization. SpaceX plans to mine Martian ice for water, split it into oxygen and hydrogen for breathable air and rocket fuel, and even extract methane from the atmosphere to power return trips. It's a blueprint for independence, treating Mars not as a destination but as a homeland. NASA's approach is more cautious, focusing on science and safety. Their proposed Mars base camp would start as a series of compact habitats, possibly 3D printed from regolith by robotic rovers before humans arrive. These wouldn't be cities, but high-tech research stations akin to Antarctica's McMurdo temporary homes for rotating crews. Radiation shielding is a top priority. NASA favors covering habitats with several meters of soil or deploying innovative materials like hydrogen-rich plastics to block cosmic rays. Food production would rely on closed-loop systems similar to those tested on the International Space Station, where every gram of waste is recycled. Unlike SpaceX's settlers, NASA astronauts likely wouldn't stay permanently. Their mission would be to unlock Mars' geological secrets, search for ancient life, and test technologies for future deep space voyages. The biggest divide isn't just scale, it's philosophy. SpaceX embraces risk, betting that rapid iteration and private funding can overcome hurdles like unproven radiation shielding or the psychological toll of isolation. NASA, bound by taxpayer dollars and political scrutiny, must prove every system works before launch. Yet both face the same brutal challenges: dust storms that clog solar panels, toxic perchlorates in the soil, and the fact that no one knows how human reproduction or child development would fare in 1/3 Earth's gravity. What's remarkable is how these visions might converge. SpaceX could provide the heavy lifting to get NASA labs to Mars, while NASA research could make Musk's city viable. Already, agencies are studying hybrid concept scientific outposts that gradually expand into colonies as technologies mature. Whether Mars becomes a research hub or a second home for our species, one thing's certain: the first footsteps there will reshape humanity's future, proving that even the harshest worlds can be tamed with enough ingenuity and grit. Most of Earth's impact threats lurk unseen in the vast darkness of space, but not for long. NASA NEO Surveyor is on a mission to shine an infrared spotlight on these hidden dangers, scanning the cosmos for asteroids that could one day cross paths with our planet. Unlike optical telescopes that rely on reflected sunlight, this space-based observatory detects heat signatures, making it impossible for even the darkest, most elusive space rocks to hide. Slated for launch in 2027, its goal is simple yet monumental: catalog at least 2/3 of near-Earth objects larger than 140 meters, the size threshold where an impact could devastate entire regions. What sets NEO Surveyor apart is its ability to spot asteroids approaching from the sun's direction, a blind spot for ground-based observatories. Picture a space rock barreling toward Earth but lost in the sun's glare until it's too late. the same scenario that caught Chelyabinsk meteor watchers off guard in 2013. Surveyors' infrared eyes cut through that glare, detecting warmth emitted by asteroids rather than relying on sunlight. Its detectors are so sensitive they could pick up a match flame's heat from across a football field, allowing it to track objects other telescopes miss. The mission's design is a masterclass in efficiency, orbiting at Lagrange point 1, a gravitational sweet spot between Earth and the Sun. It will sweep the sky in a slow, methodical pattern, covering the most likely paths of hazardous objects. Each detection gets logged into a growing database, helping astronomers predict orbits decades in advance. But Surveyor isn't just a lookout, it's a planetary defense scout. By characterizing asteroid compositions, whether they're solid metal, loose rubble piles, or ice-rich bodies, it informs how we might deflect future threats. A rubble pile might shatter if hit too hard, while a metallic asteroid could require gentler nudges. Critics argue that spending millions on asteroid hunting is excessive when no imminent threats are known, but history suggests otherwise. The Tunguska event of 1908 flattened 800 square miles of Siberian forest with a blast rivaling a nuclear bomb, while the dinosaur-killing Chicxulub impactor was likely 10 kilometers wide. Surveyors' proponents stress that even a single overlooked object could rewrite human history, and with enough warning, missions like DART could alter its course. Beyond defense, the telescope will unveil secrets about our solar system's formation. Many near-Earth asteroids are time capsules from the planetary construction phase, their orbits shuffled by Jupiter's gravity over eons. Surveyors' data could reveal how water and organic materials hitchhiked across the solar system, potentially seeding life on Earth. It might even spot interstellar interlopers like Oumuamua, helping us gauge how common such visitors are. The clock is ticking. Congress mandated NASA to find 90% of threatening near-Earth objects by 2020, a deadline missed due to funding gaps. NEO Surveyor represents a second chance, a sentinel poised to give humanity the ultimate luxury, time to react. Every asteroid it spots and tracks is one less cosmic surprise, turning existential threats into manageable challenges. In a universe where extinction lurks in the shadows, this telescope isn't just an instrument, it's an insurance policy for civilization itself. While most spacecraft focus on destinations within our solar system, the Johns Hopkins Interstellar Probe dares to go further, much further. This audacious mission is designed to do what only two human-made objects have achieved before: break free from the Sun's gravitational grasp and sail into the uncharted territory of interstellar space. But unlike Voyager 1 and 2, which stumbled into the cosmic beyond as their missions expanded, this probe is built from the ground up for a singular purpose: to study the mysterious boundary where our solar system ends and the galaxy begins. With a planned 50-year journey, it's not just a spacecraft, it's a time capsule of human ingenuity, carrying instruments that will still be relaying data long after many of its creators have passed away. The mission's primary target is the heliosphere, that invisible bubble of charged particles blown outward by the solar wind. Think of it as the Sun's protective force field, shielding us from harsh galactic cosmic rays. But right now, we know shockingly little about its shape, size, or how it interacts with interstellar space. The Interstellar Probe will map this boundary in unprecedented detail, using suites of sensors to measure magnetic fields, plasma waves, and high-energy particles. Some theories suggest the heliosphere resembles a quasar, while others argue it's more like a comet's tail. Only this mission can settle the debate with hard data. What makes this probe revolutionary isn't just where it's going, but how fast it'll get there. Using a gravity assist from Jupiter, it's designed to reach speeds of up to 7 astronomical units per year, roughly twice as fast as the Voyagers. That means it could cross into interstellar space in less than 15 years, compared to the 36 it took Voyager 1. This blistering pace comes from cutting-edge propulsion and an ultra-lightweight design, allowing it to carry more advanced instruments than its predecessors. Unlike the Voyagers, which were built with 1970s technology, this probe will pack modern spectrometers, plasma analyzers, and even a dust detector capable of sniffing out individual atoms from other star systems. But speed isn't the only advantage. The mission is engineered for longevity, with a nuclear power source designed to last half a century. That's crucial because interstellar space holds secrets that unfold over decades. Picture this: as the probe ventures farther, it'll sense subtle shifts in the density and temperature of interstellar plasma, revealing how our solar system moves through the Milky Way's local cloud. It might even detect the faint pressure wave of a nearby supernova or the gravitational tug of undiscovered objects in the Oort cloud. Every year beyond the heliosphere will provide a fresh dataset, letting scientists construct a 3D map of our cosmic neighborhood for the first time. The mission's legacy won't just be scientific, it's philosophical. By the time the probe's signal finally fades beyond detection, its discoveries could redefine humanity's place in the galaxy. Did other star systems form with similar protective bubbles? Are we sailing through an unusually dense patch of interstellar material, or is this the norm? Answers to these questions won't just satisfy curiosity, they'll help us predict the long-term habitability of Earth and other worlds. And who knows, if another civilization ever stumbles upon this silent traveler, its carefully chosen payload might tell them everything they need to know about the species that dared to reach beyond their cradle. Beneath Enceladus' shimmering ice shell, a hidden ocean erupts into space through towering geysers, spraying its secrets where any passing spacecraft might taste them. That's the daring premise behind the Enceladus Orbiter, a proposed NAS, a mission that could finally answer whether life exists beyond Earth, not by drilling through miles of ice, but by catching cosmic snowflakes. Imagine a spacecraft that first orbits Saturn's sixth largest moon, diving through its icy plumes to analyze their chemistry, then transforms into a lander, touching down near those erupting fractures to study fresh deposits. It's a two-in-one marvel designed to hunt for biosignatures where they're most accessible, in the frozen spray of an alien ocean. What makes Enceladus unique isn't just its subsurface sea, it's how extravagantly it shares its content. Cassini's discoveries in the 2000s revealed geysers blasting water vapor, organic molecules, and even silica nanoparticles into space, telltale signs of hydrothermal activity on the seafloor. The Orbiter's spectrometers would comb through these particles, searching for amino acids with patterns that hint at biological origins. But the real coup would be detecting lipids or complex polymers, molecules too intricate to form easily through non-living chemistry. Picture the lander's microscope spotting cell-like structures in ice grains, their membranes intact despite the journey from ocean to surface. Landing on Enceladus presents a ballet of precision. The spacecraft would target the moon's tiger stripes, those famous fissures near the South Pole where plumes erupt most violently. Unlike Mars rovers navigating rocky terrain, this lander must perch on ice as slippery as glass, possibly using harpoons or heated feet to anchor itself. Its instruments would study freshly fallen plume material, delicate organics that might degrade if exposed to Saturn's radiation for too long. Some designs even include a robotic arm to scoop ice directly from fissure walls, where ocean material may coat the surface like frost. The mission's orbital phase is equally audacious. Flying just 50 kilometers above the surface, lower than most commercial jets, the spacecraft would map Enceladus' gravity field to pinpoint where the ocean lies closest to the ice. But the showstopper, its mass spectrometers would perform on-the-fly analysis of plume particles, separating salts from organics with precision surpassing Cassini's vintage instruments. One tantalizing target, hydrogen cyanide, a toxic compound that nonetheless acts as a cornerstone molecule for probiotic chemistry. Finding it here would suggest Enceladus ocean isn't just habitable, it's a factory for life's building blocks. Beyond biology, the Orblander could crack planetary mysteries. Its seismometers might listen for icequakes revealing the ocean's depth, while thermal probes measure heat flow from the moon's core. Combined with plume data, this could confirm whether Enceladus has alkaline vents like Earth's lost city, a habitat where some scientists believe life originated. The implications stretch far beyond Saturn. If this tiny moon can sustain chemistry complex enough for life, similar processes could unfold on Europa, Titan, or even exoplanet ice worlds. The clock is ticking for this mission concept. Enceladus plumes are seasonal, and some models suggest they may quieten in the coming decades as the moon's orbit shifts. Catching them at their most active could mean the difference between sampling a living ocean and staring at frozen silence. If selected, the Orblander wouldn't just be another spacecraft, it'd be humanity's most sophisticated alien detective, parsing ice crystals for the faintest whispers of life in the dark. Imagine a world where reaching space is as simple as stepping into an elevator and pressing up. This isn't the plot of a sci-fi novel, it's the audacious promise of space elevators, a concept that could slash the cost of launching payloads from thousands of dollars per pound to pocket change. The idea is deceptively simple, a cable anchored to Earth's surface stretching tens of thousands of miles into space, held taut by centrifugal force and a counterweight beyond geostationary orbit. Up and down this cosmic tether, robotic climbers would ferry cargo, satellites, and even astronauts, ditching the need for explosive rocket fuel altogether. But the engineering challenges, they're as towering as the elevator itself. The key lies in materials stronger than anything nature has ever produced. Traditional steel would snap under its own weight long before reaching orbit, which is why scientists are pinning their hopes on carbon nanotubes, microscopic threads with tensile strength 100 times greater than steel. Picture a ribbon woven from billions of these nanotubes, thinner than paper yet capable of supporting climbers hauling tons of cargo. Labs have grown strands a few feet long, but scaling up to 22,000 miles. That's like trying to spin a fishing line from New York to Sydney without a single weak point. Even a single flawed nanotube could unravel the entire structure under stress, sending the elevator crashing down in a catastrophic failure. But what if we built our elevator somewhere with less gravity? Enter the Lunar space elevator, a shorter, more achievable cousin tethered to the moon. With only 1/6 of Earth's gravity, the cable wouldn't need nearly as much strength, and existing materials like Xylon or Kevlar might suffice. Anchored near the moon's equator, it could stretch 50,000 kilometers toward Earth, terminating at a floating platform in high orbit. This wouldn't just be a lunar lifeline, it'd be an interplanetary shipping lane. Mining robots could send rare metals mined from the moon's surface to Earth's orbit without a single rocket launch, while spacecraft could dock at the platform to refuel before journeying deeper into the solar system. Some designs even propose using the elevator as a slingshot, flinging payloads toward Mars with pinpoint precision. The obstacles go beyond materials. A terrestrial elevator would face hurricanes, space debris, and even sabotage risks. Its anchor point would need to hover near the equator, where hurricanes are rarest, and the cable would require constant adjustments to dodge satellites and orbital junk. Then there's the power problem. Climbers can't rely on cords in a vacuum, so engineers propose beaming energy via lasers or microwaves, a technology still in its infancy. And who regulates this megastructure? If a space elevator exists, every nation on Earth would have a stake in controlling it, potentially sparking a new era of cosmic geopolitics. Yet the payoff could rewrite the rules of spaceflight. Launch costs, currently averaging $60 million per Falcon 9 flight, might drop to a fraction of that, opening access to startups, researchers, and even tourists. Asteroid mining would shift from fantasy to feasibility, with elevators hauling platinum and water ice back to Earth orbit. And for interplanetary travel, spacecraft could launch already in orbit, free from Earth's gravity well, needing only a fraction of the fuel they'd require today. The environmental impact alone is staggering. No more rocket exhaust polluting the upper atmosphere, no more discarded boosters cluttering the oceans. What makes space elevators so tantalizing isn't just their potential, but their inevitability in the eyes of their champions. The International Academy of Astronautics predicts a prototype could emerge within this century, while Japan's Obayashi Corporation has pledged to build one by 2050. Whether it's nanotubes or some yet undiscovered metamaterial that gets us there, the dream persists because the alternative, burning tons of fuel to escape our planet, feels increasingly archaic. The elevator isn't just a transportation device, it's a symbol of humanity's refusal to be bound by the limits of rocketry, a declaration that the stars might one day be reached not with a roar, but with the hum of a climber ascending a thread to the sky. While NASA and the European Space Agency painstakingly choreograph their multi-decade Mars sample return ballet, China is quietly scripting its own blockbuster Tianwen-3, a daring two-launch mission that could beat the West to delivering red planet rocks to Earth. This isn't just a scientific endeavor, it's a high-stakes demonstration of China's accelerating space prowess, executed with a streamlined efficiency that's rewriting the rules of interplanetary logistics. The Chinese plan cuts through complexity like a scalpel. Instead of relying on a rover to cache samples over years, Tianwen-3 will deploy a single lander equipped with a drill capable of burrowing 2 meters below Mars' surface, deep enough to reach pristine material untouched by radiation. Within days, it'll pack these geological treasures into a soccer ball-sized ascent vehicle, which will blast off directly to an awaiting orbiter. No fetch rovers, no planetary relay races, just a swift grab-and-go operation. That orbiter then becomes the cosmic courier, ferrying the samples home by 2031, potentially arriving before NASA Perseverance-derived haul. What makes this approach revolutionary isn't just its speed, it's the risk calculus. NASA's strategy spreads risk across multiple missions, but China's condensed timeline means fewer variables, fewer points of failure. Their secret weapon, the proven Long March 10 rocket, adapted from their Lunar program and capable of hurling heavier payloads toward Mars than most Western counterparts. And while NASA collaborates internationally, China's closed-loop system lander ascent vehicle, Orbiter, keeps everything in-house, avoiding the diplomatic tangles of shared technology. Geopolitically, Tianwen-3 is a flare shot across the bow. Mars has become the new arena for superpower rivalry, with sample return as the ultimate prestige project. Whoever delivers Martian soil first claims bragging rights in the history books and possibly patents on any novel materials or biological clues found within. There's also the subtle messaging. China's ability to execute complex deep space missions independently undermines the long-held Western monopoly on interplanetary exploration. Yet the mission's real genius lies in its secondary objectives. While drilling, the lander will analyze subsurface water ice, a resource critical for future Chinese crewed missions hinted at in their 2061 Mars exploration roadmap. And unlike NASA's obsession with ancient biosignatures, China seems equally focused on practical concerns: radiation levels, soil mechanics, and in situ resource utilization. It's exploration with an eye toward colonization, blending pure science with strategic foothold building. The contrast in philosophies couldn't be sharper. Where NASA Mars sample return resembles a meticulous archaeological dig, China's plays like a special forces extraction, swift, targeted, leaving little to chance. Both have merit, but only one might claim the prize first. As these parallel missions unfold, they're doing more than retrieving rocks. They're testing which vision of space exploration will dominate the coming century. collaborative but cautious, or solo and audacious? The answer may lie in who gets their samples home first and what secrets those red-stained grains ultimately reveal. Hidden among the blinding glare of distant stars, countless Earth-like worlds may orbit just out of sight until now. NASA's proposed Habitable Exoplanet Observatory, or HAB-X, aims to rip away that celestial curtain with a revolutionary starlight-suppressing coronagraph, an instrument so precise it could spot the faint glow of an ocean or the spectral signature of a forest on a planet dozens of light-years away. Unlike previous telescopes that infer planets through indirect methods, HAB-X would deliver direct images of these alien worlds, transforming tiny dots into rich landscapes ripe for scientific scrutiny. At the heart of this mission lies an optical marvel, a coronagraph advanced enough to dim a star's light by a factor of 10 billion, like spotting a firefly hovering next to a lighthouse. Traditional coronagraphs struggle with stars merely 100 times brighter than their planets, but HAB-X's design pushes this ratio into uncharted territory. The secret, a series of precisely shaped mirrors and masks that redirect starlight away from the detector with nanometer-scale precision, while allowing the faint planetary light to pass through. Imagine holding up a cosmic thumb to block the sun, but with such accuracy that you could still see the wings of a butterfly fluttering near its edge. This isn't just incremental improvement, it's a quantum leap in our ability to isolate planetary signals from stellar noise. But HAB-X's ambitions go beyond mere photography. Its suite of spectrographs would dissect the light from these exoplanets, hunting for chemical fingerprints of habitability, oxygen, water vapor, methane, and even industrial pollutants like chlorofluorocarbons that could hint at technological civilizations. One tantalizing target, a planet orbiting Proxima Centauri, where HAB-X might detect the telltale red edge of vegetation, the same spectral signature Earth's forests leave in satellite images. Another priority, systems like TRAPPIST-1, where multiple Earth-sized worlds crowd their star's habitable zone. HAB-X could determine whether these planets are barren rocks or water-rich oases by measuring atmospheric water absorption bands with unprecedented clarity. The telescope's design reflects lessons learned from predecessors, with a 4-meter segmented mirror smaller than James Webb's but optimized for stability. It would operate at Lagrange point 2, far from Earth's interfering glow. Unlike Webb's folded origami approach, HAB-X would launch fully deployed, its sunflower-shaped starshade unfurling to 16 meters in diameter. This starshade, flying 40,000 kilometers ahead of the telescope, would cast an ultra-precise shadow, blocking starlight before it even reaches the primary mirror. Together with the coronagraph, this dual-system approach creates redundancy. If one fails, the other can still deliver groundbreaking science. What makes HAB-X truly transformative is its potential to move beyond statistics into specifics. Current missions like Kepler and TESS have revealed that Earth-sized planets are common, but HAB-X would reveal what kind of Earths they are: desert worlds, ice planets, or perhaps something resembling our own blue marble. It might even catch weather patterns in action, tracking cloud movements or seasonal changes on planets with years as short as weeks. For the first time, we wouldn't just be counting exoplanets, we'd be studying their climates, geology, and potential biology as if they were neighbors in our own solar system. Critics argue that HAB-X's multi-billion-dollar price tag is steep for a single-purpose observatory, but supporters counter that its scientific payoff could redefine humanity's cosmic perspective. Finding an Earth twin with signs of life, even microbial, would answer one of our species' oldest questions: are we alone? And if HAB-X surveys dozens of habitable zone planets only to find them sterile, that null result would be equally profound, suggesting Earth's vibrant biosphere might be rarer than we ever imagined. The telescope's development is still in the concept phase, competing with other flagship missions, but its technology is already being tested in vacuum chambers and simulated space environments. Every laser-aligned mirror and vibration-damped optical bench brings us closer to an era where alien sunrises aren't just imagined, but measured, analyzed, and perhaps one day even glimpsed in vivid detail. The moon's poles hold a treasure far more valuable than gold water ice lurking in craters untouched by sunlight for billions of years. These permanently shadowed regions could become the gasoline stations of space, fueling everything from lunar bases to Mars-bound ships. That's why India's Chandrayaan-4 and NASA's Viper rover are gearing up for an unprecedented treasure hunt, probing these frosty vaults with technology so precise it could detect a single snowflake in a football field of dust. Chandrayaan-4 marks India's boldest lunar leap yet, a mission designed to land within a kilometer of the moon's south pole, where temperatures plummet to -250°C. Unlike previous landers that relied on solar power, this craft will pack radioisotope heaters to survive the long lunar nights, allowing it to drill into the regolith and extract core samples that could contain ice crystals. But the real innovation lies in its mini rover, equipped with a laser spectrometer that can vaporize tiny patches of soil on contact and instantly analyze their chemical makeup. Picture a robotic prospector zapping the lunar surface like a cosmic geologist, mapping water concentrations in real time across this frozen desert. Meanwhile, NASA's Viper, short for Volatile's Investigating Polar Exploration rover, takes a more mobile approach. Slated to touch down in 2024, this golf cart-sized robot will roam for 100 days, using a 1-meter drill nicknamed the Trident to bore into shadowed areas at different depths. What makes Viper revolutionary isn't just its drilling prowess, but its ability to sense water molecules even when they're bound up in minerals rather than pure ice. Its neutron spectrometer can detect hydrogen atoms hiding in the soil, while infrared sensors map surface temperatures to predict where ice might lurk just centimeters below. The stakes couldn't be higher. Water isn't just for drinking split into hydrogen and oxygen, it becomes rocket fuel. Calculations suggest a single cubic meter of lunar ice could yield enough propellant to send a small payload back to Earth. Establish an ice mining outpost, and suddenly the moon transforms from a destination into an interplanetary pit stop. But harvesting this resource demands precision. Sunlight exposure or improper handling could cause priceless ice to sublimate into space before it's utilized. That's why both missions will test extraction techniques, from baking soil in ovens to capture vapor to using cryogenic traps that freeze released gases back into containers. Beyond practicality, these missions could rewrite lunar history. The ice isn't just frozen water, it's a time capsule containing solar wind particles and comet debris accumulated over eons. Analyzing its isotopic ratios might reveal whether Earth's oceans originated from ancient asteroid impacts, or if the moon preserved unique chemistry lost on our geologically active planet. Some theories even suggest the poles might harbor organic compounds delivered by comets, hinting at how life's building blocks spread through the solar system. What makes this duo special is their complementary strengths. While Viper focuses on resource mapping for future astronauts, Chandrayaan-4's precise sampling could uncover fundamental science about the ice's origins. Together, they're pioneering the first steps toward off-world resource utilization, a concept that could make moon bases economically sustainable. Imagine a not-so-distant future where lunar ice mines power orbital fuel depots, and rockets bound for Mars top off their tanks using propellant mined from these shadowed craters. Every drill core analyzed, every ice patch mapped by these robotic pioneers brings that vision closer to reality, proving that the moon's greatest value might not lie in what we find there, but in what it enables us to become, a species no longer bound to a single world. SpaceX's Starlink Gen 2 constellation is a paradox wrapped in a revolution, a network of tens of thousands of satellites promising to beam high-speed internet to every corner of the globe. while simultaneously sparking fears of turning Earth's orbit into an impassable junkyard. With over 4,000 satellites already circling the planet and plans to launch 30,000 more, this isn't just an upgrade. It's a complete reimagining of how humanity interacts with the sky. On one hand, it's bridging the digital divide, bringing connectivity to remote villages, ships at sea, and disaster zones where traditional infrastructure fails. On the other, astronomers warn that these reflective satellites are photobombing telescope observations, leaving streaks of light that obscure distant galaxies and potentially blinding sensitive instruments to incoming asteroids. The technology behind Starlink Gen 2 pushes boundaries most companies wouldn't dare approach. Each satellite now sports laser links that create an orbital mesh network, allowing data to hop seamlessly between satellites without ground station handoffs. That means a farmer in rural Kenya can video call with latency lower than a New Yorker's cable connection. But what makes this system truly disruptive is its funding model. Every dollar earned from internet subscriptions fuels SpaceX's far more audacious goal, building a self-sustaining city on Mars. Elon Musk has openly admitted that Starlink's profits are the financial engine for Starship development, turning a global internet service into the ultimate cosmic crowdfunding campaign. Yet the trade-offs are impossible to ignore. Critics point to near misses between Starlink satellites and other spacecraft, warning of a potential Kessler syndrome scenario where cascading collisions render low Earth orbit unusable for generations. SpaceX counters that Gen 2 satellites are designed with automatic collision avoidance and end-of-life deorbiting systems, ensuring they burn up harmlessly in the atmosphere. But with other companies like Amazon's Project Kuiper and China's Guowang planning their own mega constellations, the skies could soon become a traffic jam of unprecedented scale. The debate extends beyond engineering into philosophy. Proponents argue that universal internet access could uplift billions, democratizing education and economic opportunity in ways akin to the invention of the printing press. Opponents see a privatized takeover of what was once considered global commons, with Silicon Valley corporations effectively writing the rulebook for orbital real estate. Regulatory agencies scrambled to keep pace, as existing space laws were drafted for an era when a few dozen satellites circled the planet, not tens of thousands. What often gets lost in the noise is how Starlink Gen 2 is quietly enabling scientific breakthroughs of its own. During Russia's invasion of Ukraine, the system provided critical comms when traditional networks were severed, showcasing its resilience. Climate scientists are exploring how its global coverage could monitor deforestation or methane leaks in real time. Even SpaceX's worst-case scenario, having to replace satellites every 5 to 7 years, could drive down launch costs through economies of scale, making space more accessible for researchers and startups. The ultimate irony, the same technology accused of cluttering Earth's orbit might one day help clean it up. SpaceX is testing SpaceTug satellites that could potentially deorbit defunct spacecraft, and the lessons learned from managing Starlink's mega constellation could inform future debris removal missions. Whether history remembers Starlink as a visionary leap or a cautionary tale depends on how humanity balances two competing truths: that connectivity is now as vital as electricity, and that the sky above us is a frontier we're only beginning to understand. Imagine a lunar night so long and cold it lasts 2 Earth weeks, where temperatures plunge to -170 degrees Celsius, a place where even the most advanced solar panels sit useless in the dark. This is the challenge NASA's fission surface power project aims to conquer, deploying compact nuclear reactors not as a last resort, but as the backbone of future Moon and Mars bases. Unlike traditional solar-dependent systems, these reactors could generate 40 kilowatts of continuous power, enough to run life support, laboratories, and even propellant production facilities through endless nights or global dust storms. The genius of these reactors lies in their simplicity. Instead of the complex cooling towers of Earth-based nuclear plants, they use passive sodium heat pipes to transfer energy from the reactor core to Stirling engines, which convert heat into electricity with eerie silence. Picture a device no larger than a refrigerator buried safely underground, radiating power without smokestacks or spinning turbines, just steady, reliable energy, whether under the relentless Martian sun or the inky blackness of a lunar crater. Each unit is designed for autonomous operation, capable of running for a decade without refueling, making them ideal for remote outposts where maintenance missions might come only once every few years. But why nuclear? Solar power seems like the obvious choice until you consider the realities of off-world environments. Mars dust storms can blot out the sun for months, while lunar nights cripple solar arrays just as astronauts need power to survive. NASA calculations show that a Mars base relying solely on solar would need 5 tons of batteries to bridge these gaps compared to a single 1-ton fission system delivering uninterrupted electricity. The reactors also dodge another solar weakness: location limitations. With nuclear, bases can operate in polar craters packed with ice reserves or lava tubes shielded from radiation sites that would leave solar-dependent crews stranded in the dark. Safety concerns might spring to mind, but these aren't Chernobyl-style behemoths. The reactors use low-enriched uranium fuel, reducing proliferation risks, and their cores are designed to shut down automatically if temperatures rise unexpectedly. In launch scenarios, the fuel remains inert until activated on site, minimizing radiation exposure during accidents. Engineers have even tested worst-case scenarios: when submerged in water or smashed onto concrete at terminal velocity, the reactors simply fail safe without meltdowns. The implications stretch far beyond keeping lights on. Reliable power enables game-changing technologies like 3D printers fabricating spare parts from local regolith, or electrolyzers splitting lunar ice into breathable oxygen and rocket fuel. On Mars, fission could energize greenhouses growing fresh food year-round, or labs analyzing soil samples for signs of ancient life without worrying about daily energy budgets. Perhaps most crucially, it unlocks the ability to scale up. Imagine a network of reactors powering entire lunar villages or fueling depots for deep space missions. What makes this project revolutionary isn't just the technology, it's the shift in mindset. For decades, space agencies treated nuclear power as a high-risk option. Now, with Artemis and Mars ambitions demanding robust solutions, fission has become the quiet powerhouse behind humanity's multiplanetary future. The first demonstrator could land on the Moon by the early 2030s, marking the moment we stopped merely surviving off-world and started thriving. Every watt generated by these reactors won't just power equipment, it'll propel the audacious idea that the harshest environments in the solar system are no match for human ingenuity. While NASA Artemis program dominates headlines, another lunar revolution is brewing, one fueled not by government funding, but by the personal ambitions of one of Earth's wealthiest individuals. Jeff Bezos's Blue Origin is betting big on the Moon with Blue Moon, a privately developed lander designed to deliver cargo and eventually crew to the lunar surface. This isn't just a spacecraft, it's a delivery truck for the off-world economy, built to haul everything from scientific instruments to construction materials for future bases. With a payload capacity rivaling small military helicopters, Blue Moon could become the workhorse of lunar logistics, ensuring Artemis astronauts arrive to find fully stocked depots waiting in the dust. What sets Blue Moon apart isn't just its payload bay, it's the philosophy behind it. While NASA focuses on exploration, Blue Origin envisions permanent infrastructure. The lander's design accommodates modular cargo containers, allowing standardized deliveries of water extractors, solar arrays, or even 3D printers that turn moon dust into bricks. Imagine a future where Blue Moon missions fly regularly, like orbital supply, runs to the International Space Station, but with lunar regolith instead of vacuum. Bezos has openly compared this vision to his time building Amazon's delivery network, only this time the customer might be a NASA outpost or a private mining operation scraping helium-3 from the Sea of Tranquility. Technologically, Blue Moon bridges old and new. Its B-7 engine burns liquid hydrogen and oxygen propellants that could one day be sourced from lunar ice, making the lander self-sustaining. But the real innovation lies in its precision landing system, which uses LiDAR and machine learning to touch down within meters of target zones, avoiding boulders or steep slopes that could topple delicate cargo. This level of accuracy is crucial for delivering habitats or fuel depots that future missions will depend on. Early versions will be uncrewed, but Blue Origin has already showcased concepts for a crew cabin variant, complete with expansive windows for lunar tourists, or more likely, geologists surveying untapped resources. The symbiosis with NASA runs deep. Blue Moon was originally developed for the agency's now cancelled Lunar Cargo program, but it's found new life as a potential complement to Artemis. While NASA, a human landing system, focuses on astronaut transport, Blue Moon could handle the unglamorous but vital work of prepositioning supplies. Picture this: ahead of a crewed Artemis mission, multiple Blue Moon landers deposit power generators, oxygen tanks, and rovers at the landing site. When astronauts arrive, their lunar home is already partially assembled, vastly extending their range and productivity. This division of labor, NASA, a leading exploration, private industry enabling sustainability, could become the model for humanity's expansion into the solar system. Yet Blue Moon's ambitions stretch far beyond being NASA, a cosmic moving van. Bezos has hinted at partnerships with companies like Ceres Robotics to integrate AI-driven construction equipment, potentially allowing the lander to deploy autonomous bulldozers that level terrain for future pads. There's even talk of adapting the design to serve as a return vehicle, using lunar-made propellant to blast samples, or eventually astronauts back into orbit for pickup. These long-term visions reveal Blue Origin's ultimate goal: not just visiting the moon, but industrializing it, turning what was once a symbol of national prestige into a hub of private enterprise. The challenges ahead mirror the scale of these aspirations. Blue Moon's hydrogen fuel requires cryogenic storage, a nightmare in the moon's wild temperature swings, and its reliance on yet-to-be-proven lunar ice mining means early missions will depend on Earth-supplied propellant. Competitors like SpaceX's Starship threaten to overshadow it with sheer payload capacity, though Blue Origin counters that their lander's smaller size makes it more cost-effective for routine deliveries. Regulatory hurdles loom too, as no framework exists for private companies to claim or monetize lunar resources they help transport. What makes Blue Moon revolutionary isn't its engineering alone, but the paradigm it represents. For the first time, a lunar vehicle is being designed not as a disposable science platform, but as the first link in a supply chain spanning two worlds. Every bolt it tightens, every solar panel it deploys, inches us closer to a future where the moon isn't just explored, it's inhabited. And while the spotlight shines on astronauts planting flags, it may well be the uncrewed cargo landers like Blue Moon that quietly build the foundations for humanity's off-world future, one payload at a time. SpaceX isn't just another space telescope, it's a cosmic cartographer on an unprecedented mission to map the entire sky in ways we've never seen before. Scheduled for launch no later than April 2025, this NASA Explorer will perform the first all-sky near-infrared spectral survey, capturing the fingerprints of over 100 million galaxies and 300 million stars in our own Milky Way. But here's what makes it extraordinary. Instead of snapping pretty pictures, SpaceX will split the light from every point it observes into 96 distinct color bands, creating a chemical barcode for the universe that reveals what celestial objects are made of, how far away they are, and how they're moving through the cosmos. The mission's core goal sounds deceptively simple. Study cosmic inflation, that brief moment less than a second after the Big Bang when the universe expanded faster than light itself. While we can't see inflation directly, its echoes linger in the large-scale structure of the cosmos. Spherex will hunt for these fingerprints by mapping galaxy distributions in 3 dimensions across 10 billion light-years. Imagine throwing a stone into a pond. The ripples spread in predictable patterns. Inflation should have created similar density waves in the early universe, and by measuring how galaxies cluster at different distances, Spherex could confirm whether our current models of these primordial ripples hold true, or if we're missing something fundamental about how spacetime itself unfolded. But the telescope's ambitions don't stop at the beginning of time. It's also rewriting the story of how galaxies evolve. Its infrared eyes can peer through cosmic dust clouds that obscure visible light, revealing stellar nurseries where new stars are born. Each of its color bands acts like a filter for specific molecules. One might highlight water ice clinging to dust grains in interstellar space, while another picks up the telltale glow of complex organic compounds. This means Spherex could trace how life's building blocks get distributed across galaxies, mapping the cosmic supply chain that delivers water and organics to newborn planetary systems. What sets Spherex apart from giants like Hubble or Webb is its scope versus precision trade-off. Where those telescopes zoom in on individual targets with exquisite detail, Spherex scans everything, like switching from a microscope to a wide-angle lens. Its modest half-meter mirror might seem small compared to Webb's 6.5-meter behemoth, but it's paired with detectors cooled to just 8 degrees above absolute zero, letting it catch the faintest infrared whispers from across the universe. The spacecraft will spin slowly as it orbits Earth, methodically painting the entire celestial sphere in stripes of data over its 2-year mission, creating a map so comprehensive it'll serve as a treasure hunt guide for future telescopes. Perhaps most intriguing are the surprises Spherex might uncover. By surveying the whole sky in infrared, it could stumble upon rare objects like rogue planets, worlds drifting between stars, or the elusive planet 9 if it exists in our outer solar system. Its spectral data might reveal unexpected molecules floating in interstellar space or catch the afterglow of distant supernova that other telescopes missed. Every patch of sky Spherex scans holds the potential for discovery, from the chemistry of asteroid belts in nearby star systems to the large-scale flows of galaxies pulled by invisible dark matter rivers. This mission embodies a new era of astronomy where big questions meet big data. The 100-terabyte catalog Spherex produces will be publicly available, letting researchers worldwide mine it for decades. Some scientists will use it to test theories of dark energy, others to plan Webb's observations of promising exoplanet atmospheres, and perhaps a graduate student somewhere will spot an anomaly that rewrites astrophysics textbooks. Spherex isn't just a telescope, it's a time machine, a chemical analyzer, and a roadmap for future exploration, all packed into a spacecraft no heavier than a small car. When it launches, we won't just be getting another space observatory. We'll gain an entirely new way of seeing the universe, one spectral barcode at a time. Imagine standing on a wind-swept Martian plain, gazing up at a hazy blue sky, not the thin, lifeless expanse we see today, but one thickened by deliberate human intervention, where liquid water flows and algae blooms in newly formed lakes. This is the audacious dream of Mars terraforming, a concept straight out of science fiction that some scientists argue could become reality within centuries. At its core lies a radical proposition that an entire dead world could be engineered into something habitable, not just by sealing humans inside domes, but by rebooting Mars' entire climate system. One of the most dramatic proposals involves jump-starting a Martian greenhouse effect using giant orbital mirrors, solar reflectors up to 250 kilometers wide positioned near the poles. These colossal structures, made of ultra-thin reflective films, would focus sunlight onto the ice caps, vaporizing trillions of tons of frozen carbon dioxide and water in a calculated chain reaction. As the CO2 enters the atmosphere, it traps heat, warming the planet further and releasing more greenhouse gases from the soil, a runaway process that might raise temperatures by 20 degrees Celsius over decades. Early prototypes could be tested with smaller mirrors targeting specific regions, like crater rims where ice deposits cluster. The mirrors themselves might seem like fantasy, but materials like aluminized mylar already exist. The challenge lies in deploying structures the size of small countries in space without tearing. Then there's the more controversial approach, manufacturing super greenhouse gases on Mars itself. Compounds like perfluorocarbons, thousands of times more effective at trapping heat than CO2, could be synthesized from Martian elements using autonomous chemical plants. Spread into the atmosphere, these gases might warm the planet enough to melt subsurface permafrost, kickstarting water cycles. The ethics here are thorny. Unlike Earth, where such chemicals are pollutants, on Mars they'd be tools for planetary-scale landscaping. Some models suggest strategically releasing just a few parts per million could trigger warming cascades with relatively small energy inputs compared to mirror projects. But warming Mars is only half the battle. Even with Earth-like temperatures, the atmosphere would remain lethally thin, about 1% of Earth's pressure, and mostly unbreathable CO2. This is where extremophile organisms enter the equation. Genetically engineered cyanobacteria or lichens could be seeded across the planet, converting atmospheric carbon into oxygen through photosynthesis over centuries. Experiments in Antarctic dry valleys and the International Space Station have already shown certain microbes can survive simulated Martian conditions, metabolizing perchlorates in the soil and releasing oxygen as a byproduct. The long game, a slow-motion biosphere engineering project where each generation of organisms modifies the environment just enough for the next more complex wave to thrive, a terraforming relay spanning millennia. Critics counter that Mars' lack of a magnetic field dooms any atmosphere we create to be stripped away by solar wind, as likely happened billions of years ago. Proponents have an equally sci-fi solution: artificial magnetospheres. One NASA study proposes placing a powerful magnetic dipole at Mars' L1 Lagrange point, creating a protective bubble that would deflect charged particles. The energy demands are staggering, equivalent to powering a small city, but advances in compact fusion or space-based solar might make it feasible. Alternatively, superconducting rings buried along Mars' equator could generate a planetary magnetic field, though the infrastructure would dwarf all human construction projects combined. What makes these theories so compelling isn't their practicality, it's their redefinition of what's possible. Terraforming forces us to think in geological time, weighing interventions that might take 500 years to show results. The very act of debating them shifts our perspective. Mars stops being a destination and becomes a project, a canvas for humanity's most ambitious creative act. Whether through mirrors, microbes, or magnetic shields, each scheme carries the same revolutionary premise: that planets aren't just places we adapt to, but worlds we can reshape in our image, provided we're willing to play the long game. Astrobotic's lunar landers are rewriting the rules of space exploration, proving that the moon isn't just for governments anymore, it's open for business. This Pittsburgh-based company has become the UPS of the cosmos, with its Peregrine and Griffin landers designed to deliver payloads to the lunar surface for a fraction of traditional mission costs. Picture a spacecraft the size of a golf cart, packed with everything from NASA science experiments to memorial capsules containing human ashes, all riding shotgun on what's essentially a cosmic delivery truck. Their first mission, Peregrine 1, nearly made history in early 2024 as the first private lunar landing, despite a propulsion leak that cut the journey short. But failure in spaceflight often teaches more than success. and Astrobotic's stumble only sharpened its roadmap for turning the moon into a thriving hub of commercial activity. What makes these missions revolutionary isn't just their private funding, it's their cargo philosophy. Unlike government landers fixated on scientific priorities, Astrobotic's payload bays are agnostic, open to universities, startups, and even artists. One upcoming flight carries a shoebox-sized rover from Carnegie Mellon, set to become the first American robot to roll on lunar regolith. Another payload includes a Bitcoin-loaded time capsule, while a third tests lunar cement made from synthetic moon dust. This eclectic mix isn't random. It's stress-testing the idea that the moon can sustain diverse economic activity beyond pure science. The company's online payload configurator even lets customers book space by the kilogram, with prices starting around $1.2 million cheaper than some luxury yachts. The real game-changer lies in Astrobotic's long-term vision, establishing the equivalent of lunar ports. Their proposed Moon Ranger outposts would serve as permanent way stations, offering power, communications, and even storage for payloads awaiting pickup. Imagine a future where mining robots deposit platinum-rich asteroids at an Astrobotic depot, while a separate lander arrives to haul the treasure back to Earth orbit. This modular approach mirrors how shipping containers revolutionized global trade, standardized, scalable, and indifferent to what's inside. The company's collaborations with SpaceX and United Launch Alliance for rideshare launches further cement this vision, creating an end-to-end supply chain from Earth factories to lunar customers. Critics argue that commercializing the moon risks turning it into a wild west of unchecked exploitation, but Astrobotic's playbook includes safeguards. Their landers incorporate NASA-sponsored navigation systems to avoid culturally significant sites like Apollo landing zones, while payloads undergo rigorous contamination reviews. There's also the question of who profits if lunar ice or rare metals become viable exports, a tension already sparking debates about whether space resources should be considered communal heritage or private property. Despite these challenges, Astrobotic's deliveries are laying the groundwork for something bigger than any single mission. Every sensor they deploy, every rover they deploy, even every symbolic trinket they carry, normalizes the idea that the moon isn't just a destination, it's a workplace, a laboratory, and eventually a home. As their landers transition from experimental to routine, they are proving that the final frontier might not be conquered by giant leaps, but by countless small packages, each one a building block for humanity's off-world future. Gravitational waves, ripples in spacetime first predicted by Einstein, have been detected on Earth, but our planet's noisy environment limits what we can observe. Enter LISA, the Laser Interferometer Space Antenna, a revolutionary mission set to launch in the mid-2030s that will turn the quiet of space into an unparalleled listening post for the universe's most violent collisions. Unlike ground-based detectors like LIGO, which catch the high-frequency chirps of stellar mass black holes, LISA trio of spacecraft will form a triangular laser array 2.5 million kilometers on each side, sensitive enough to detect the deep, cosmic hum of supermassive black holes merging at the centers of galaxies. The engineering behind LISA is mind-bending. Each spacecraft will fire infrared lasers at the others, creating a precise measurement grid capable of spotting distortions smaller than the width of an atom over those vast distances. Picture this: as a gravitational wave passes through the solar system, it subtly warps space-time, causing one arm of LISA triangle to stretch while another compresses. The lasers detect these changes with picometer precision, equivalent to measuring the distance to Pluto accurate to within a hair's width. This isn't just an upgrade to Earth-based observatories, it's an entirely new sense organ for humanity, tuned to frequencies we've never before been able to hear. LISA primary targets are the mergers of black holes millions of times heavier than our Sun, events so colossal they shake the fabric of space-time itself. These cosmic behemoths don't collide with a visible flash. Their dance is dark, announced only by their gravitational signatures. By tracking their spirals, LISA could reveal how supermassive black holes grow, whether they're born large or accumulate mass through mergers, and even test if Einstein's general relativity holds true under such extreme conditions. Some theories suggest these mergers might produce unexpected echoes, hints of extra dimensions or quantum gravity, effects that only LISA sensitivity could catch. But the mission's potential goes beyond black holes. It might detect the faint gravitational whispers of stars orbiting Milky Way's central black hole, SGRA, or catch the early moments of binary white dwarfs spiraling toward collision. There's even a chance LISA could stumble upon cosmic strings, hypothetical defects in spacetime left over from the Big Bang. If they exist, every new source would rewrite astrophysics textbooks, turning gravitational waves from a curiosity into a fundamental tool for exploring the universe. What makes LISA especially exciting is how it complements other observatories. A supermassive black hole merger detected by LISA could cue telescopes to scan the region for electromagnetic counterparts, creating a multi-messenger view of the event. This synergy could solve long-standing mysteries, like whether these mergers trigger quasar activity or if they're always dark affairs. The mission's decade-plus lifespan means it could track some binaries for years before their final collision, offering a front-row seat to spacetime's most extreme transformations. The road to launch isn't without hurdles. LISA must counteract forces like solar radiation pressure on its spacecraft with micro-thrusters, maintaining their positions within a tolerance finer than a virus's width. Its laser links require stabilization so precise that test missions like LISA Pathfinder have already spent years perfecting the technology. Yet every challenge overcome proves something profound, that humanity isn't confined to observing the cosmos from our noisy planetary perch. With LISA, we're planting ears in the silent depths of space, ready to eavesdrop on the universe's grandest symphonies, ones composed not in light or sound, but in the bending of spacetime itself. Venus might seem like the last place humanity would settle. Its surface is a scorching hellscape hot enough to melt lead, with crushing atmospheric pressures and sulfuric acid rains. But look 50 kilometers above that inferno, and something extraordinary emerges. A layer of the Venusian atmosphere where the temperature and pressure are almost shockingly Earth-like. Here, NASA, a high-altitude Venus operational concept HAVOC, rebranded as HISES, proposes a vision straight out of science fiction: floating cities suspended in the clouds, where humans could live and work in giant, helium-filled airships. The numbers tell a surprising story. At that altitude, temperatures hover around 25 degrees Celsius room temperature by Earth standards, while atmospheric pressure matches Earth's at sea level. The carbon dioxide-rich air could be processed into breathable oxygen, and solar panels would bask in uninterrupted sunlight above the reflective cloud layer, generating more power than equivalent panels on Earth. Even radiation exposure is lower than on Mars thanks to Venus's thick atmospheric blanket. Scientists call it the Goldilocks zone of Venus, not too hot, not too cold, just right for sustained human presence. The HISES concept revolves around massive, dirigible-like habitats filled with breathable air, which would naturally float in Venus's dense CO2 atmosphere like bubbles in soda. These wouldn't be small research stations, but expansive, modular colonies. Some designs envision structures spanning kilometers, with interconnected pods for living quarters, greenhouses, and labs. Unlike Mars habitats buried underground to avoid radiation, Venusian colonies would ride the gentle winds of the upper atmosphere, circling the planet every few Earth days with minimal energy expenditure. Imagine stepping onto an observation deck and seeing endless golden clouds stretching to the horizon, lit by a diffused sunbeam piercing the haze. But living in the clouds comes with daunting challenges. Sulfuric acid aerosols would eat away at unprotected materials, requiring specialized coatings or scrubbing systems to keep the airships intact. Storms in the Venusian atmosphere, while not as violent as Earth's hurricanes, could still jostle stations unpredictably. Then there's the question of supply lines. Unlike Mars, where resources might eventually be mined locally, Venus offers little accessible water or minerals in its upper atmosphere, meaning everything from spare parts to drinking water would need to be shipped from Earth or extracted through chemical processes from the acidic clouds. The most audacious part, HICES isn't just theory. Prototype technologies are already being tested here on Earth. NASA Venus Atmosphere Maneuverable Platform (VAMP), a drone designed to cruise the Venusian skies, has undergone flight tests in conditions simulating the planet's upper atmosphere. Meanwhile, researchers are experimenting with acid-resistant aerogels and self-healing materials that could repair small breaches autonomously. The key to making this sustainable lies in closed-loop systems, algae bioreactors that convert CO2 into oxygen, or filters that extract trace water vapor from the atmosphere. If perfected, these technologies could turn floating cities from a wild idea into a viable outpost. Why Venus at all? The planet offers unique advantages. Solar power is abundant and reliable, unlike on Mars where dust storms can black out panels for months. The thick atmosphere provides natural shielding from cosmic rays, reducing cancer risks for long-term residents. And from a strategic standpoint, Venus's proximity to Earth allows for shorter travel times, just 5 months with current propulsion, compared to 6 to 9 months for Mars. Some scientists even speculate that Venus's upper atmosphere could serve as a testing ground for technologies later used in the harsher environments of gas giant moons or exoplanets. The HICES vision forces us to rethink what colonization means. Instead of adapting to a planet's surface, we'd adapt to its skies, building not on rock but in the air itself. It challenges the assumption that habitability requires solid ground, suggesting instead that humanity's future might lie in floating ecosystems untethered to any world. Every technical hurdle overcome brings us closer to a reality where cities don't just orbit planets, they float within them, riding the currents of alien skies. Unlike Mars missions focused on terraforming, Venus colonization would embrace its environment rather than fight it, a lesson that might shape how we approach other hostile worlds. If successful, these floating habitats could become more than scientific outposts. They'd be proof that life can thrive in the most unexpected corners of the cosmos. The dream isn't to conquer Venus, but to harmonize with it, turning its most forgiving layer into a sanctuary among the clouds. Pulsed plasma rockets sound like something ripped from the pages of a pulp sci-fi novel. But this theoretical propulsion system could become the key to unlocking the solar system. Unlike traditional chemical rockets that burn fuel in short, explosive bursts, these engines would generate continuous thrust by superheating gas into a scorching plasma and blasting it outward at staggering speeds. The result, a spacecraft that accelerates steadily for weeks or months, reaching velocities that could slash a Mars voyage from the current 7-month slog to a brisk 1 or 2 month sprint. Imagine boarding a ship in Earth orbit and arriving at the red planet before a terrestrial ocean liner crosses the Atlantic. The secret lies in the rocket's ability to sustain thrust over extended periods. Chemical engines, even advanced ones like SpaceX's Raptor, can only fire for minutes before exhausting their fuel, leaving spacecraft to coast most of the way to Mars. Pulsed plasma rockets, by contrast, might run for months on just kilograms of propellant, thanks to their mind-bending efficiency. They work by ionizing argon or xenon gas with high-frequency radio waves, transforming it into a magnetically confined plasma hotter than the sun's surface. Magnetic nozzles then direct this plasma into a focused jet, achieving exhaust velocities 10 times faster than conventional engines. To put that in perspective, where a chemical rocket might top out at 5 kilometers per second, a pulsed plasma system could reach 50, enough to rewrite the rules of interplanetary travel. But speed isn't the only advantage. These engines could dramatically reduce radiation exposure for astronauts, one of the biggest hurdles for crewed Mars missions. Galactic cosmic rays pose a constant threat in deep space, and the shorter the trip, the less time spent bathing in this invisible storm. There's also the psychological benefit. Compressing the journey to just 60 days would ease the mental strain of confinement, making Mars feel more like a long-haul flight than an epic odyssey. Cargo missions could benefit even more, with unmanned freighters making multiple round trips per Earth-Mars synodic cycle, effectively turning the red planet into a logistical neighbor rather than a distant outpost. The concept isn't entirely untested. Small-scale plasma thrusters already propel satellites in Earth orbit, and NASA's 2013 Vasmer experiments proved sustained plasma acceleration in a vacuum. The leap to interplanetary propulsion hinges on scaling up these systems while solving the power problem. A Mars-bound plasma rocket would require a nuclear reactor or massive solar arrays infrastructure that doesn't yet exist in space. Thermal management is another hurdle. Containing million-degree plasma without melting the engine demands materials that can withstand conditions harsher than a re-entry vehicle's heat shield. Visionaries at companies like Ad Astra Rocket Company are tackling these challenges head-on. Their designs suggest modular engines that could be assembled in orbit, with superconducting magnets to contain the plasma and heat-resistant ceramics lining the thrust chamber. Early simulations show that a 1-megawatt plasma rocket could propel a 50-ton habitat to Mars in 70 days, assuming continuous acceleration for the first half of the trip followed by a gradual deceleration. That's still slower than sci-fi's warp drives, but it's a seismic shift from today's ballistic trajectories. What makes pulsed plasma so revolutionary isn't just the technology, it's the paradigm shift. Traditional rocket science treats propulsion as a brief, fiery event at the start of a journey. Plasma rockets reimagine it as a sustained process, turning the void between planets into a highway where speed is limited only by how long the engine stays on. If perfected, this could open destinations beyond Mars. Imagine 6-month trips to Saturn's moons instead of 7-year slogs, or fast-track missions to mine metallic asteroids. The solar system wouldn't just be within reach, it'd be within routine commuting distance. Yet for all its promise, plasma propulsion faces a catch-22. To prove itself, it needs a high-profile mission like a crewed Mars flight, but agencies won't greenlight such missions until the tech matures. Breaking this deadlock might require a middle step, like testing a scaled-down version on lunar supply runs or asteroid surveys. Every successful firing in deep space would bring us closer to an era where Mars isn't a distant dream, but a regular stop on humanity's interplanetary itinerary. The challenges are immense, but so is the payoff, a future where the stars feel just a little bit closer. Oumuamua wasn't just another space rock, it was a cosmic puzzle wrapped in an enigma. This interstellar visitor, the first ever detected passing through our solar system, behaved like nothing astronomers had seen before. It accelerated away from the sun as if pushed by some unseen force, its bizarre elongated shape tumbling end over end like a celestial cigar. But before scientists could train their best telescopes for a closer look, it vanished into the void, leaving behind tantalizing questions. Now, cutting-edge mission concepts are emerging to ensure we never miss another opportunity like this again. Missions designed to chase down the next interstellar wanderer, dock with it, and decode its secrets in real time. One radical proposal comes from Project Lyra, a blueprint for a spacecraft that could intercept an object like Oumuamua within years of detection. The plan leverages gravity assists around Jupiter and the Sun to slingshot a probe up to 60 astronomical units per year, speeds that would make even the Voyagers jealous. But here's the twist. Instead of relying on traditional chemical rockets, Lyra's architects envision a hybrid propulsion system combining solar sails for initial acceleration with compact nuclear electric thrusters for fine-tuning the approach. Picture a spacecraft unfurling a sail the size of a football field to catch sunlight, then switching to ion engines once the target is near, maneuvering to match velocities with an object that might be moving twice as fast as anything we've ever landed on. The real challenge isn't just catching these cosmic speedsters, it's figuring out what to do once we're there. Oumuamua's bizarre properties hinted at possibilities ranging from a fragment of a Pluto-like exoplanet to, more controversially, an artificial light sail from another civilization. Future missions would need a Swiss Army knife of instruments, spectrometers to sniff out exotic ices, LiDAR to map unprecedented shapes, and even microscopes to analyze dust clinging to the visitor's surface. Some designs include harpoons and drills to secure samples, while others propose deploying tiny sensor pods that could stick to the object like cosmic burrs, transmitting data even if the main spacecraft can't maintain contact. What makes these missions so urgent is the statistical reality. There are likely thousands of interstellar objects passing unnoticed through our solar system every year. New telescopes like the Vera Rubin Observatory will spot dozens annually, giving scientists their first real catalogue of cosmic nomads. But without pre-positioned interceptors ready to launch at a moment's notice, these discoveries will remain fleeting curiosities rather than world-changing insights. That's why astronomers are pushing for a dedicated interstellar object response program, a standing fleet of spacecraft with modular payloads that could launch within weeks of a promising detection. The implications stretch far beyond astrophysics. If we discover that objects like Oumuamua carry water or organic molecules, they could be cosmic couriers delivering life's building blocks between star systems. Alternatively, finding even one with unmistakable signs of technology would rewrite humanity's place in the universe. Every mission designed to chase these visitors carries the same thrilling possibility that one day we might catch up to something not just from another solar system, but from another civilization's hand. Until then, each blueprint and prototype brings us closer to the day when an interstellar object doesn't slip away, but instead becomes an open book waiting to be read. Unlike traditional planetary science that studies familiar worlds, these missions embrace the unknown with every bolt and sensor. They acknowledge that the greatest discoveries might not come from the planets we can predict, but from the unexpected travelers that pass through our cosmic neighborhood without warning. The next Oumuamua could be spotted tomorrow, and this time we'll be ready. From lunar cities to interstellar probes, these 30 missions aren't just pushing boundaries, they're redrawing the map of what's possible. Each one carries the potential to rewrite textbooks, reshape economies, and even redefine humanity's place in the cosmos. Take Mars sample return. Those tiny tubes of red dust could hold evidence that life isn't unique to Earth. Or consider Europa Clipper, poised to sniff out plumes from a hidden ocean that might swarm with alien microbes. On the engineering front, projects like space-based solar power could wean our planet off fossil fuels, while lunar ice mines might become the interplanetary gas stations of tomorrow. And let's not forget the big thinkers' breakthrough Starshot aiming for Alpha Centauri, or the wild vision of Venusian cloud cities floating in sulfuric acid skies. What ties these missions together isn't just their ambition, but their ripple effects. A discovery on Enceladus could revolutionize biology. LISA gravitational wave detection might unveil hidden dimensions. Even failures will teach us volumes. Every crashed lander, every broken drill bit adds to our knowledge for the next attempt. This isn't just about planting flags or collecting data. It's about forging pathways that future generations will walk. The children born today might take their first off-world vacations in Blue Origin's lunar landers, or pursue PhDs studying atmospheric spectra from HabX's Earth-like exoplanets. Now it's your turn. Which of these cosmic game changers fires your imagination? Is it the gritty practicality of nuclear reactors on the moon, or the poetic audacity of catching a ride on a light sail to another star? Drop your pick in the comments and debate what we should prioritize as a species. And if you want front row seats to humanity's next giant leaps, hit subscribe. We're just getting started. The universe has spent 13.8 billion years setting the stage. Now it's our turn to step into the spotlight.